This conference will now be recorded.
Hi, everybody. It's March 31st. This is Jack. It's 3:30 in the afternoon. I have notified all of you about today's lecture, and I do encourage that anybody can call in and participate in real time on these conferences, but I realize you guys have many things going on. All right. So today I'm going to talk about sediment management in the Colorado River and the Grand Canyon region. The reason this is important is that now we're making the shift from having spent more than a month talking about water supply considerations and how that affects operations of the dams and the river, to now talking about the environmental side of the equation. And you're going to see that although water supply continues and will always drive the major management decisions for the Colorado River, environmental considerations do in fact make a difference. And you're going to see that any dam operator has to consider these issues. So if every one of you who is a civil engineer who might aspire to work in the area of water resource engineering, I'm going to try to convince you or demonstrate to you how the environmental issues affect how you operate facilities. And if you're a natural resources student taking this class, I'm going to try to show you how your science affects reservoir operations, and you might think about how to effectively communicate your science when you communicate with reservoir operators. All right, let's get started. This is a photograph of the upper end of Lake Powell. Here is the end of the old boat ramp, and elevation 3,700, which is a full Lake Powell, would be somewhere where my cursor is depicted. And the reservoir had greatly reduced in its elevation and storage between the end of 1999 and June 2003 when this photograph was taken. In fact, the reservoir had declined enough that the National Park Service had to build a new access and a new temporary marina down here so that boats could still access and put boats in here at the Height Marina. But everyone knew that someday the reservoir would be full again and this boat ramp could be used. In 1980, when Lake Powell was full, I did a Cataract Canyon trip, and we ended our trip by pulling our boats out on this boat ramp and de-rigging our boats as houseboats and motorboats were putting in. A year later, here's what Lake Powell looked like. The reservoir continued to go down. The marina here was completely abandoned. And in fact, the takeout for river trips was around the bend here. All of this is the sediment carried by the Colorado River out of Cataract Canyon and deposited at the head of Lake Powell. The next year, much of those delta sediments had been overgrown by tamarisk and willow. And this is the area where the reservoir goes up and down. But my main purpose in showing you this is to illustrate the magnitude of sediment deposition. Let's look at this plot for a minute by Lincoln Pratzen and colleagues from Duke, who undertook a oceanographic type survey of the bottom topography of Lake Powell in 2004 and 2005, and then plotted their data on previous data about previous surveys of Lake Powell. In the horizontal axis is the distance upstream from Glen Canyon Dam, right here at 0. And the distance is measured sort of along the center line of the Colorado River in Glen Canyon. You can see in this black line, this is the trace of the Colorado River before Glen Canyon Dam was completed. That's the river. That's what the river looked like. Very steep here in the rapids of Cataract Canyon. And the distance between this gray line and this purple line is the fine sediment that accumulated between the closure of the dam in 1963 and 1976. And between the gray line and the blue line, all of this is the sediment that filled Lake Powell during the era up through when the reservoir was full. This is the similar plot going up the San Juan arm of Lake Powell. You can see somewhat less sediment, but actually a delta front that seems to go much further downstream. Here you can see the elevation of the penstocks. Here you can see the elevation of the river outlets. Here you can see the reservation of Full Pool. And you can see here in blue is the elevation in 2005, the lowest that Lake Powell has gotten since it's filled. A couple things to note here. First off, this is the pattern of how any reservoir fills with sediment. The river comes through, the sediment drops out and forms a delta. Notice that the reservoir sediments collect far upstream from the dam, and there's essentially 200 kilometers between the delta and the dam way down here. You can see that the sediments in the San Juan Delta are actually a little bit closer, but still 100 kilometers from the dam. But you can see that there is some collection from bottom currents called turbidity currents, which have brought very fine mud to Lake Powell. But this is a pattern, and this is how Lake Powell will fill up with sediment someday, by this delta moving closer and closer to the dam. What does this mean for releases from the dam? This means that the water released here into the Grand Canyon is devoid of sediment, because all of the sediment carried by the Colorado River drops in here, and the water released from the dam down here is crystal clear. Let's look at the Grand Canyon. The width of these arrows is sort of proportional to the average sediment loads of the modern Paria River and the modern Little Colorado River, where we have modern data. And the size of this arrow is proportional to the pre-Glen Canyon Dam amount of sediment that would have come through Glen Canyon and into the Grand Canyon. 57 million tons a year of sand and silt and clay, somewhat more mud, silt and clay, than sand. Today, all of this sediment is now trapped in Lake Powell, and this is the amount of sediment on average that comes into Grand Canyon during the period of modern measurements. The Paria River brings in certainly much less mud than the Little Colorado River, a bigger river, but the Paria River brings in more sand than does the Little Colorado River. Why? because the watershed of the Paria River is different from the Little Colorado River. There's much more sandy terrain, and so the Paria River is a supplier of sand, and I've given you a couple of the values associated with these deliveries. In the 15 miles between Glen Canyon Dam and the Paria River, right here, between the dam and the blue dot, the only water flowing through here is crystal clear water. This is a remaining part of Glen Canyon. And if you release crystal clear water into what was once a sand-bedded stream, and you have virtually no sediment except tiny amounts coming in from little tributaries, then the river has been able to erode its bed deeply into its former channel. And that's reflected in this graph, in which this green line, the solid green line, is the bed of this 15-mile or 25-kilometer long reach of Glen Canyon before Glen Canyon Dam was built. And here in the green dashed line is sort of a typical water surface at average flows. Boring showed that in blue here, much of the bed was sand, in blue and black. I guess the colors have changed. And below that was gravel. 40 years of dam operations of releasing clear water into this Glen Canyon reach has eroded the bed from this green line to this red line as much as 3 to 5 meters of erosion. So the bed of the river is now the bed of the river is now much lower than it once was. What does that do? Well, here's a typical cross section. Notice that the river bed is now lower than it once was. I'm just going to check on something now. No, okay, I can't. No, I can't. I'm just going to see if I can. I guess I can't. I wanted to see if I could. There we go. All right, this is better. So the river bed is lower. So erosion immediately below Glen Canyon Dam has occurred because you're releasing clear water through. Notice the water surface of a typical discharge now in the red line is lower than it was in green. So the riverbed has sort of dropped, and the water surface of typical flows have dropped. So think about the ecological implications of this. If the river channel drops and decreases and erodes, that means that the average flow doesn't get as high. And then because of flood control, which we've talked about before, Glen Canyon Dam doesn't release the big floods it once did. So the sum of the two is that the riverbed is lower, and then flood control means the floods don't get as high. The net effect of that is that the riparian zones of the pre-dam river have been completely abandoned. They never get any water anymore. And a new riparian zone much lower to the river has developed. So these are significant ecological changes. The other ecological change is to strip out all the sand from Glen Canyon. The river now flows on gravel. So you've changed a sand-bedded river to a gravel-bedded river. A gravel-bedded river is something non-native trout love. In Grand Canyon, many of the sandy beaches in Grand Canyon have been eroded away in some of the most vulnerable places, although sediment has accumulated in the rapids between these eddy sandbars. So up in Glen Canyon, there's been erosion along the whole reach and disconnection of the riparian zone from the modern river and the creation of a new riparian zone. In Grand Canyon, the riverbed hasn't dropped because the river is held up by all the boulders and all the rapids, but the sandbars that intervene between the rapids, many of them have eroded away, and others of those have at least gotten smaller. There are still nooks and crannies of sand left. The sandbars are not nearly as extensive as they once were, but these little bits of sand are the bits of sand that campers and river runners camp on and are the remaining vestige of these former big sandbars. One thing you may never have thought about is that big open sandbars, like what used to exist in Grand Canyon, would have been sources of sand that when heavy springtime winds would blow, it would pick the sand up and blow it up on the surrounding hillsides. That's what you see here. Some of these wind-blown dunes bury archaeological sites and archaeological resources and protect them from vandalism or just falling down. And the amount of sand replenishment up to these high surfaces has now been cut off because the sandbars are smaller and the vegetation sort of intercepts the wind-blown sand. So in summary, the resource value of these sandbars is that the bars are now used as river campsites. The shape of these sandbars sort of forms the architecture of aquatic habitat that is of value to some fish species. Although the pre-dam river was largely devoid of riparian vegetation, fine-grained sediments are something that riparian vegetation can grow on, so it at least is of interest as a potential substrate. There is this linkage with archaeological sites, and then also just sediment in the river creates a turbid river, and a turbid river is one of the distinctive attributes of the river that the native fishery developed in. I'm going to stop here, close this, and then begin, take a break and stretch your legs, and then we're going to start again on some new material about how to restore this.
This conference will now be recorded.
All right. This is now part 2 of this lecture. Here I'm going to talk about modern post-dam management of sediment in the Colorado River. Here's a photograph of the Colorado looking like the river for which it was named, a Rio Colorado, a reddish, brownish river. You're looking at the river during a controlled flood release that occurred during the last 10 years. You can see a stream gauger and a cableway on a platform that's suspended by cable. You can see a boat down here catching the samplers. The samplers are lowered to the bottom of the river and then up to the water surface. You can see a supply boat here providing support. Here's an old USGS gauging station. This is at a spot in the Upper Granite Gorge. You can hike to this spot by going down the Kaibab Trail. Well, we have eroding sandbars in the Grand Canyon. Why not just add more sediment to the river? In fact, that has been studied, and the Bureau of Reclamation did a reconnaissance study of what would be involved to add something on the order of 4 million tons a year of sand to the river. That sand would have been dredged at a tributary called Navajo Canyon, and a slurry pipeline that would have floated below the water surface would have been routed down the reservoir and then over the dam, and then either dumped fine sediment in right at Glen Canyon Dam or 15 miles downstream at Lee's Ferry. That's a reconnaissance engineering study by the Bureau of Reclamation. Tim Randall was the lead author. Estimated that the capital cost would be about $220 million if the pipeline discharged sediment right at the dam, and about twice as much if it discharged at Lee's Ferry. Why would one ever go to the trouble of routing the sediment 15 extra miles and therefore not resupply sediment in Glen Canyon, where I just showed you there's been 3 to 5 meters of bed erosion? Why not put sand back in? Why? Because trout fishermen don't want sediment back in. They like the new transformed environment. And that, of course, was this challenge that you guys read about in the last assignment in my article, Science and Values in Restoring the Grand Canyon. Some people like one thing. Some people like relics of the past, like sandbars. Other people like artifacts of dams, like a trophy trout fishery. I just want you to know that these engineering studies have been done. There is not consensus to spend this kind of money. And so these studies just sit on the shelves, not implemented. For point of reference, asking the question, is it a big number or a small number? The annual budget of the Grand Canyon Monitoring and Research Center is $10 million a year. So there you go. Carly Payne, thank you for joining.
Hi, Jack.
Carly, hi, Carly. I'm talking to this is as if I feel like I'm the Stephen Colbert show, and we're saying recorded in front of a live audience. So this is recorded in front of a live audience of one. Carly, thanks for being there. I just did a little half an hour on the resources of sediment, and now I'm talking about what to do about it. So so on we go.
Awesome.
Great. So this is a release of a controlled flood release from Glen Canyon Dam. This one was taken this photo was taken in, I think, 2008. That's Secretary of the Interior Dirk Kempthorne. This is quite a deal when this water comes blowing out like this, when all 4 of the river outlets are going. It's quite an energizing thing. And were it not for the coronavirus, we would have stood here and looked at all of this on our tour. I have asked you to read, and I have posted this article called Origins of the Controlled Flood, in which I tell the story of the politics and science between getting the first flood in 1996 implemented. But the main thing I want you to see here is I want you to see that this is crystal clear water. There's no sediment in it. So that seems pretty goofy, right? How do you use clear water to build a sediment resource? You'd think you needed sediment, right?
Right.
On these three graphs, 1996, 2004, and 2008, what I've shown here is what the natural flood through Grand Canyon would have looked like if there was no Glen Canyon Dam. And here's in 2008 what that flood would have looked like, a bigger water year, 2004, a tiny year. And then in black is what the actual releases from Glen Canyon Dam were. And these are the controlled floods I'm talking about, here, here, and here. The first point is, I want you to see that a controlled flood looks nothing like a natural flood. Don't kid yourself and think that these simulated floods out of Glen Canyon Dam simulate the true long environmental disturbance of the natural river, whether it be a big flood year or a little one. And I just want you to see that. Now, oops, let me do this. All right, here we go. What is not going on here? All right. So what I want to talk about is, for a minute, is this flood here in 1996. This was the first time we ran this flood, and I've suggested you read this paper to learn politically how we accomplished getting this particular flood to occur, how we forced the political system into having this. Once we had this, and this flood lasted 7 days, we learned some things so that we adapted management to go from this sort of a design to this one. And there are subtle differences between this and this and this, and that's what I'm going to talk about now. So this is the hydrograph of the first flood in 1996. And what I'm talking about now is described in this short article by Dave Rubin and others, which I have also posted and that I've asked you to read. So the two things I've asked you to read is the Schmidt et al. 1999 and the Rubin et al. 2002. This is the hydrograph. This is the water flow. So what does this say? This tells us that the water flow rose precipitously, was high for 7 days, didn't change for 7 days, and then the flow receded. These dots are different places where the suspended sediment transport was measured. Different places, different samplers, but no matter where the measurements were made, you can see that on day 1 and 2, the amount of sediment in the river and the turbidity and how much sediment was there was much higher. And as the flood went on, the river got clearer and the amount of sediment in transport decreased. Carly, can you think of a reason why, if the flow never changes, why the amount of sediment being transported would decrease?
Was it? Oh, I don't know.
Okay, so here's one thing. So if you think about it, and I realize you may not have taken the geomorphology class, but here's the thing. The flow is dead steady. So what you can think about is the hydraulic forces, right, that can move the sediment, that's not changing. So it's not like the flood is getting bigger and so it has more force to move more sediment. So if the amount of force that the river has to move sediment doesn't change, but the amounts of sediment in the river plummeted. So if it's not that the forces have changed, it's that it plummeted because there was no more sediment left to move. In other words, the sediment was blown down to Lake Mead in the first day or two. Some of the sediment was caught in eddies, And then there was background sediment at much lower rates as the flood proceeded. Does that make sense, Carly?
Yeah, it does. So the sediment had just
Yeah,
cleared out by then.
exactly, exactly. And the mud cleared out first. So we thought, and I was one of the guys who designed this, we thought that these dots would stay constant because we had all the sediment in the world on the bed of the river. So this was a huge shocker when it was like, whoops, there's much less sediment. So this was scary to us because it said, uh-oh, you can run a flood too long, because what you're trying to do is when the concentrations are really high, then most of the sediment goes to Lake Mead, but bits of the sediment get caught in eddies. Let me show you an example of this. You know, Colorado River and Grand Canyon is like a glorified pipe. It's a scenic pipe. It's a scenic ditch, but it's just a pipe. And when fine sediment comes in from the Paria River, from one of these natural desert tributaries, it goes kerplop on the bed of the river. Meanwhile, above the river are those sandbars that people camp on. And so the Paria rivers come in, the sediment is sitting kerplop on the bed of the river. What we've learned is that if we do nothing, that sand on the bed of river hops, skips, and jumps its way 250 miles downstream to Lake Mead. And we never know it because it always stays on the bed of the river, and this is what we're camping on. But we'd like to make these things bigger. So we release crystal clear water from Lake Powell, and 15 miles downstream, we have these patches of sand on the bed of the river that have come in from this tributary, the Paria River. So we have a flood. It stirs up this sand here. And then when the river goes back down from flood, we hope that some of the sand that was in the bottom of the river got caught in these eddies here, while the rest of it went down to Lake Mead. If we get it wrong, then we run a flood that lasts too long, and we not only clear the bed of the river out, we also erode out the patches of sand. So to go back through this is the condition right after the Paria River dumps in sediment. We run a flood, stir up the sediment. If I was really doing this artistically, I would color this water brown, not blue. We make the river brown, and then when the river goes down, we've cleared the river of sand on the bed, but we hope that we've caught some sand in the eddies to make the eddy sand a little bit bigger. And if we do it wrong, we make them smaller rather than bigger. And if we go back to this, if we run a flood too long and we're out here, that's bad, because that gives the potential that we could be doing more harm than good to the eddy sandbars. And so what we learned was that we wanted to make these controlled floods only as many days as the concentrations were high, and we couldn't make them too long or we would do more harm than good. Now, this is the confluence. This is, again, a place we would have gone to on our field trip. Here is Lee's Ferry. Here's the cableway. Here's the boat ramp. Here's some boats where people were going to launch on a river trip. And here's the Paria River. And you can see that even here, the river is flowing a little bit, and the river is a little milkier and cloudier here, and it's crystal clear here. So when we have a controlled flood, we release the water out of Glen Canyon. It comes roaring down here. And then when we get to this point at 15 miles, from there on, we're stirring up sand on the bed of the river down here that's come out of this tributary. And then we hope that when we do that, we stir up sediment and we rebuild eddy sandbars down here all the way through and on down to the south. Carly, does that make any remote sense?
Yeah, I think so.
Can you think of a question that would make it more sensible?
I guess I'll just try and restate what I think you're saying. So the
Sure,
water
please.
coming out of Glen Canyon is basically crystal clear, right? And
Correct.
and then when it at the confluence with the Paria, then there's a lot more sediment coming in, and so you're just looking at how that's being transported.
In fact, the Paria River is the only source of sediment.
Okay.
Yep. So actually, let me go back here. Hold on a second. It's actually super helpful, Carly, that you're on the phone, and I really appreciate that you would do this. And I promise to get this over with by 4:30. Okay. I showed these in my in the previous remarks before you got on the phone. Carly, here's a map of the sand and mud that used to go through Grand Canyon before the dam was completed. 57 million tons a year of sand and mud came downstream out of the upper basin. And 2.3 million tons of fine sediment came out of the Paria, and 5.1 million tons came out of the Little Colorado River. So 5.1 and 2.3, that's sort of a number like, well, there it is. Actually it's 7.3. I haven't changed this number, but it's a number like 7 comes out of these two tribs versus 57 came out of here. Once the dam was completed, you cut all this out. This is zero. This is the only sources of sediment now coming to the Grand Canyon because it's zero coming out of here. So what you're doing is you're releasing floodwaters out of here. It's crystal clear to this point. And then you're trying to mobilize this sand, this 900,000 tons of sand that comes in out of the Paria, gets dumped on the bed here. Then you're trying to stir it up, build eddy sandbars all the way along. You got a little bit more to work with below here. Most of that sediment goes all the way through to Lake Mead, but you're hoping that you build up some sandbars on the way. Does that help?
Yeah, that makes sense.
Okay. So now if we go back here, let me just remind us of what the landscape of the Paria River watershed looks like. Some of you in the class may have backpacked through the Paria Narrows down here. That's a spectacular hike. Some of you have been to Bryce Canyon National Park. It's a wonderful world of geologic celebration, and the place is falling apart. And it produces a hell of a lot of sediment. And that's the sediment that goes to the Grand Canyon and becomes sandbars. So this is the protocol. Let's look at this for a minute. This is the protocol. This is the rule that we now live by in operating Glen Canyon Dam. And I would say that this rule was proposed by the Department of Interior in the last administration. It was one of the greatest accomplishments of the last administration, was to get everybody to agree to implement this rule. It was a great political achievement. I got to be involved in implementing these floods when I was chief, and it's one of the things that I'm very proud of. But the idea to do this came out of the Interior Department of the last administration. Here is time: July, August, September, and October. what's happening weather-wise and climate-wise, Carly, in southern Utah in the late summer and early fall?
It's very hot, but it's probably starting to cool down a little bit.
Okay, what about precipitation?
Oh, I guess, would it be starting to rain more, or would it still be pretty
There
dry?
you go. It's what we call the monsoon season. It's the
Oh, okay.
time of year when you don't want to be in a slot canyon in Zion National Park because you might drown. And
Okay.
that's the time of year, that the Paria River has its flash floods. So the Paria River has its flash floods in July, August, September, and October. So that's the time of year that the sediment comes in here. And so this is sort of average numbers of the amount of average sediment that comes in out of the Paria during the monsoon season. And so what we came up with was a protocol that said, we're going to measure how much sediment comes in from the Paria River down by those flash floods. And if enough comes in, then we're going to count that sediment up, and then we're going to run a flood in November to mobilize this stuff. So we're going to measure it. So in other words, it's coming in here in the monsoon season. It goes kerplop. It accumulates for a couple months, and then in November, we run a flood out of here for a couple days and mobilize that and build the sandbars. And so we have a season of inflow of sediment, a season when a flood might occur. The same thing might occur in springtime with spring rains, although it rarely does. And if it does, we would have a spring flood. But mostly the action is this fall period. Does that make sense?
Yes, that makes sense.
Okay. So I'm just going to quickly show what this requires is a wonderful collaboration between river scientists and river engineers. And I really want to emphasize this to all of us in the class who are working at the interface between river science and river engineering. This is a bunch of geomorphologists and hydrologists of the USGS desperately out here measuring. Look at this chocolate soup of the Paria River, measuring the concentration of suspended sediment in this thick soup, and there are all kinds of gauges. And so all during the monsoon season, the gaugers are running out here to make these measurements to figure out how much sediment, how much water is in the river. And then down in the Grand Canyon itself, we have special acoustic sensors to measure the concentration of sediment in the water. Most of it it's camouflaged so as not to affect the wilderness feel of the river. Up and hidden behind rocks are solar panels and transmission lines. So all of the data collected at these sensors can be uploaded to satellites and received at the USGS office. Every once in a while, people go down the river and make measurements, so they can take real measurements with bottles of water with suspended sediment, calibrated to acoustic signals, and get estimates of how much the river is carrying. So this is all river scientists in action. And then this is all served up on websites, and we calculate and we transparently display all these data, and we calculate budgets for different parts of Grand Canyon, and we say there's this much sand in this reach, and then river sediment transport engineers and river geomorphologists have built models that predict how much sediment would be transported by a flood of a particular amount. And so these are just modeling runs of how much sediment in hundreds of thousands of tons would be transported by all these possible floods. A one-day flood whose peak was 31,000 cubic feet per second. A one-day flood where the floods were a little bit higher. A 96-hour flood. Oh, excuse me. That's a 1-hour flood. That's a 96-hour flood at 45,000. So this is a much higher release, larger release from Glen Canyon Dam that lasts many more days. This is a very short 1-hour 1-hour blast, and you can see that we model this and we sort of estimate how much sediment could be transported by floods, and then we go back to our estimates of how much sediment is there available to be moved, and we start running estimates with uncertainty of what kind of a flood would mobilize just the amount of sediment that was delivered. We don't want the flood to last any longer than we have sediment there. If we ran a flood for too long, that would do harm rather than good. And you can think about this. You can think about the real challenge to science here. If I write a paper and it gets disproved later, nobody really cares. It's just a paper, right? And somebody else will write a paper and say, oh, Schmidt was wrong. But if we run a flood that's too long or too high and we blow apart the sandbars at Grand Canyon National Park, that's not like getting a paper wrong. That's like really screwing up, a national resource. So you can't really get it wrong. Does that make sense, Carly?
Yeah, it does.
The stakes are pretty high. That's my point. And this is really a wonderful collaboration of science and engineering to get it right. And so we do this, and out of all this, we end up with an agreed upon, all the agencies get together with the Grand Canyon Monitoring and Research Center, and we say, okay, we're going to have a flood of this magnitude and this duration, and that'll do the good, and everybody takes a big gulp. And then you say, okay, we're going to do it, and we're going to have it occur in November. So that's how it works. Now, of course, and I show this picture, this is something else we would have seen on our field trip. Here's a power plant at Glen Canyon Dam. 8 different turbine units. Water flows through these turbines, spins, and generates electricity. To generate a flood of 31,500 cubic feet per second, all these turbines have to be working. Well, Glen Canyon Dam is 50 years old. These turbines are starting to have to be rehabilitated because they need maintenance, because all mechanical things wear out. And in red are different months of a past year when I was running the show, when we couldn't get that much water out of the dam because one of these turbines wasn't active because it was being rehabilitated. It's a reminder that you can do all of the science and figure out what's the best thing to do for natural resources, and then all of a sudden you get some engineering constraint, and there's no way around it. And so these are the limitations on how much water you could actually release in capacity, and you'd like these numbers to be 31,500. You can see that during this period of active rehabilitation of the turbines, there never was a year that all 8 turbines were working. Something was always down, and we couldn't actually ever run a flood as big as we wanted it. Anyway, yeah.
So the goal is to have all turbines running. Like there's not one that they just keep as a backup that doesn't run?
That is correct. When Glen Canyon Dam is running full bore to maximize its power production, all 8 turbines are running. That is correct.
Okay.
Yep. So let's just look at this. This is the month of November. This is the month of November. This is one of the years we ran a flood. This is just one of the years I was down there at UCMRC. Nothing's changed since I've left. And this is what Glen Canyon Dam would have been like, up and down and up and down and up and down every day in the month of November. And then suddenly we say, and so this is all the engineering planning. This is the result. Here's one way to think about this. This is the result of people running CRSS models and then getting on the phone to Clayton Palmer from Western Area Power, and they negotiate how much water is going to be delivered and how much electricity is going to be delivered every day. So this is sort of best engineering practice. And then this is like, oh, the river guys and the restoration guys want to run a flood. And oh, there's a lot of sediment that's come in from the Paria River. We're going to have a flood. And so suddenly, this is how best engineering practices to maximize for water supply and electricity suddenly get compromised to do some good for the environment. And this dashed line is a maximum capacity of the power plant, which in this year was only 22,000 because there were other turbines that were being rehabilitated. So all of the water above the dash line here, all of that water went through the river outlet tubes and did not go through the turbines and did not generate electricity. In other words, from some people would view that this was wasted water because all of this water was wasted. It was just sent downstream without generating electricity. Does that make sense, Carly?
Yeah, it does.
Yep. So if we just quickly continue then, if you release this extra water, you can see that in the month of November, you had to release more total volume in the month than you would have here, because the area under the curve here is more than the area under the curve here, which means that in terms of doing all of this careful modeling in CRSS, it all goes out the window because you suddenly had to run this flood and release more water in November to create the flood. But the rules of the Colorado River Compact and the law of the river say the total amount for the year has to be the same, which means if you're going to release more water in one month, you got to release less water in a different month because you still have to have the same amount of water released all year long. Does that make sense?
Yeah, it does.
Yeah.
So just
Yeah. So go ahead.
So they're just redistributing the flow, basically.
Exactly. But what I want to illustrate to you is, even though we've spent 2 or 3 months in this class talking about all these utilitarian ways to operate dams, and we're spending all this time inside CRSS, and we're talking about water supply and meeting society's needs, now I'm showing you how society is willing to compromise some of these efforts to not run things with maximum engineering efficiency and say the environment matters. And that's what I'm trying to illustrate here. Okay, I just have a couple more slides. Well, this is what good it does. And I'll send you a link. I'll post a link to where you can look at a bunch of slides. But this is sort of before and after a flood in 2012. And this is before and after a flood in 2013. So you might have said, oh, well, I'd have really hoped maybe you could have shown me a picture where we increase them a little bit more than that. But I would just say the results are modest. And the controversy is shown in these years. The flood this is a different place, and every place responds a little differently. We had a flood, it increased the sandbar to here. But it cost us between $1 and $2 million in lost power revenues. Then, between the flood of 2014 and the next year, we went back to normal operations and the sandbar eroded back to this. Then we had a flood and we built it to this, and it cost $2 million in lost hydropower revenue. And then it eroded back to this, and then we had a flood and it built it to this. And so these are the goods of the benefit, but the unavoidable erosion occurs between the floods. That's an issue of public policy, and we have lost hydropower revenue. I don't really have at this point, what I love to do with you guys is just say it's really complicated and there's never winners and losers. And that was the essence of that other article that you read that I wrote, which said, you got to decide what you want because there are no simple answers. This is the amount of sediment that has been brought in by the Paria River each year. And in red stars are the years in stars are the years we had floods. In red stars are the years we had fall floods, and in green is the one year we had a spring flood. What I want you to see here is that there are years when it's really rainy in southern Utah and lots of flash floods, and years it doesn't rain at all. It's a dry year like last year. We only can have the floods when we have big years, and we've had lots of good years lately, but not every year. So we don't actually do these flood releases every year. So there we are. It's 4:30. Here are the 3 questions that I've asked you to provide. Write me a paragraph or 2 in answer to these. What proportion of the average annual pre-dam fine sediment load that once went through Marble Canyon is now trapped in Lake Powell? This just inspires you to look back at the slides and make a tiny little calculation. Here, I just ask you to repeat back what I just explained. If you release clear water out of the dam that has no sediment in it, how in the world do you use clear water to build a sediment resource? And then what did we learn from the 1996 flood that led to the change in the protocol to create this high flow experiment protocol, which is what we live by today? And these answers are in the Rubin et al. 2002 article. And this is also in the Schmidt 1999 article. I've posted an article that I wrote that's in an edited volume by Mellis, and I'm not asking you to read it, but there might be some answers and figures in there that are there as well. So that's the material for today. And Carly, do you have any questions?
I guess kind of a basic question that maybe you touched on before I joined, but is the purpose of building sandbars exclusively for boaters?
You are great in so this is the last slide I showed just before you came on. This is a 1920s era photo of Badger Creek Rapids. It's a world of muddy water, rocks and sand, and scraggly riparian vegetation. It's not, that's what the world of Grand Canyon looked like. These big sandbars are the big abundant campsites for boaters, and there is a substantial constituency for campsites and boating because 25,000 people a year go down the river by boat. And you remember that Grand Canyon River Guides, as well as the environmental organizations, are stakeholders in the Glen Canyon Dam Adaptive Management Program. There is a linkage between the distribution of these sand deposits and aquatic habitat. Although this linkage is not very strong, and we used to think it was a stronger linkage than it is. But maybe there's something unknowable that says that the distribution of these sandbars might have something to do with aquatic habitat. The fine-grained sediment is what the riparian vegetation grows out of, although the world of before the dam had very little riparian vegetation. But it is what the substrate of what riparian vegetation there was there. And then this sand also buries archaeological resources, or the sand is a source to blow up here and bury archaeological resources. And without replenishment, the archaeological resources get exposed and erode. And then a turbid river affects the aquatic ecosystem because some of the non-natives are site feeders, and therefore they're able their predation effects on the natives can be greater in clear water than turbidity. So there are other reasons, but it would be silly to not point out that campsites are first among equals.
Okay. Thank you.
You bet. All right. We're going to shut down, Carly, and we'll stop recording and turn off. Track me down if you got any other questions. We'll have another lecture later this week on fish and fish management in Grand Canyon. Take care.
You too.